Well, in review, we've just finished looking at forces. Forces cause accelerations. Accelerations cause velocities, and velocities cause changes in displacement, and that's what motion really is. So we have some tools now to describe motion and also some tools to explain motion. Forces cause motion, ultimately. Now we're going to look at more complex problem solving that involves forces. Today we're going to look at forces that are applied at a single point. So all the forces are pushing together at one spot, kind of like this. Maybe one is pulling or something like that. And then later on we're going to look at forces that are parallel to each other, that are pushing on a body at different spots. And that's a little bit more complicated, and we have to introduce another concept there. One of the best tools for solving these kinds of problems is something called a Freebody Diagram, an FBD. Physics teachers will often abbreviate this, FBD. Important tool for analyzing the forces that are in any object. What it is really is just a picture, that's all it is. But it's not a picture that's meant to be an exact portrayal of everything that you see. It's supposed to be a model of the physics behind the situation. In these free-body diagrams, forces are depicted as vectors, and that makes our analysis simpler. Vectors, remember, have both direction and size, and you can draw that on these pictures. Here's some hints for drawing free-body diagrams. For one thing, eliminate irrelevant details. I mean, it's kind of cute to draw a dog or whatever is part of the problem, but really it's irrelevant to the physics. You want to simplify your drawing and just stick to what's important, primarily vectors. When you're drawing free-body diagrams, you're going to display forces on these objects, and the only forces that can get a vector, the only forces that can act on an object, are either going to come from direct contact with another object or another source that we'll discuss in a minute. So here's what I mean by direct contact with another object. Let's say the problem says a man is pushing a large ball of snow. So here's a large ball of snow, and here's the man, and he's pushing that large ball of snow. That's direct contact with another object. So there's equal and opposite forces. That's one kind of force. And then there are three specific kinds of non-contact forces that can show up on free body diagrams. One of them is the force that's due to gravity, the one that causes gravitational acceleration. Then we also have experience in real life with magnetic non-contact forces. The magnet doesn't have to be touching it to cause this to happen. And then the third one is electrostatic. And we probably all experienced this too. You charge up some object, like you rub a comb across a piece of fur and it gains this charge and it can pull small pieces of paper toward it. It's a little experiment that science geek type kids always do. Well, all of these three forces are non-contact. They can cause things to change their motion. They're forces, but they don't have to be touching to make that happen. These two we're not going to see right now, except maybe in passing reference. But that one will be significant. One really common problem that I want to just point out here so that people don't get a tendency to do it is just because an object is moving doesn't mean it has to have a force on it. If there's no acceleration, there's no force. And so people will commonly make this mistake. They know there's a ball, let's say, and the ball is moving, it's got some velocity, and they have to say F speed, force of speed. They have to somehow put a force on there because we're used to living in a world where there's friction, and we know that in order to keep things moving at constant speed, we have to provide force. But we're going to simplify life. We're going to often say that if you're moving at a constant speed, there is no force. And in fact, in real life and in theoretical life, if you're moving at constant speed, there's no net force. So there's no F speed. Just because something's moving doesn't mean it has to have a force on it. Here's an example of a free body diagram that I'm going to draw here. Let's look at the facts of this case. We've got an eagle that's lifting a fish. And constant acceleration. Okay, there's something to take note of. It's a constant acceleration. So it is being accelerated. There's a net force on it from a lake. As this happens, he flies forward at a constant speed. So the fish has not got any force on it going forward because it's moving at constant speed. Force only accompanies acceleration. So we draw a free body diagram of the fish. Well, first of all, I'm not going to draw a fish. Partly because I'm not as good of an artist as some of you, and you might draw a little fish there, but I'm just going to stick with the very simple facts of the physics problem here. That's what a free body diagram is for. So my fish is just going to be that dot. Now I know that there's some force lifting this up from the lake that comes from the eagle. I'm going to call that Fe for force eagle. I also know that there's weight, F due to gravity, or Fg, on the fish. So the weight of the fish is pulling down, the force of the eagle is pulling up. And it says there's acceleration from the lake, so that means, in this case, the force of the eagle must be bigger than the force of gravity. Otherwise, it would not be accelerating in an upward direction. Now, in this axis, nothing at all. It's moving forward at constant speed, so there is no net force. Here's another possible situation we could draw a free body diagram for. It says a pickup truck, a snowmobile, and an ATV are all hitched up to each other at 120-degree angles. So let's imagine this to be the hitch point where all of them are hitched up to each other. And I'm going to draw the pickup truck, only, of course, I'm not going to draw a pickup truck. I'm going to draw the relevant physics, and that is that it pulls with 24,000 newtons. The snowmobile pulls with 5,000 newtons, and I'm going to model that by pointing down here, 5,000 newtons, and the ATV, 6,200 newtons. So I'm going to draw that up here, 6,200 newtons. And it says they're at 120-degree angles to each other, and that's also relevant in free body diagrams, the locations of these vectors, to call those out. So these are all 120-degree angles. That's a free body diagram on this situation. Now, this is a free body diagram that's meant to solve a problem. The question here is, what is the net force on the three vehicles? So we're going to take a look at three ways to solve this problem. First of all, just draw it out, graphical analysis. Secondly, I'm going to resolve the three vectors into components that only go on two axes. And then third of all, I'm going to take a look at the law of cosines and law of sines as a method of problem solving. So I'm going to give you three methods. You can use the one that works best for you, but I recommend the second method. I'm going to start drawing a free body diagram here. The origin of my two axes, I'm just going to call that the hitch point, where all three of these vehicles are hitched together. And I'm going to draw a line starting there, and I'm just going to head straight east, and I'm going to call that the direction that the pickup is going. Now I can actually specify in this drawing package how long I want this, so I'm going to select, if you look down in the lower left-hand corner, you'll see me select 2.400 meters, and I'm going to call that my my line, my vector, that's 24,000 newtons. Okay, now I want to go 120 degrees from there, so I'll put my protractor on here, and I will stretch it around 120 degrees, and I will select that angle right there, and I'm going to draw my second vector, and this is the one that represents the snowmobile. The snowmobile's 6,200 newtons. So I'll draw a line. I'm going to head out there, and I'm going to specify a length of 0.620, and that's going to represent my 6,200 newtons. So that line segment is drawn. That represents that vector. I'm going to put my protractor back on here, and again, going from the direction that the pickup is, but now in the opposite direction, I'm going to sweep around 120 degrees and lay myself a scale there. So now I'm going to draw my last vector. It's going to be along that axis, and I'm going to specify that it's 0.500 meters long to represent my 5,000 newtons that the ATV pulls with. Now, what I really want to do here is draw, this is the tip of this vector. I'm going to draw tail to tip to tail to tip until I've got all three of my vectors lined up. So I'm going to just transpose this vector right here. I'm going to move it down here. To make it easier to visualize, I'm going to change a setting here. Now those vectors show up a little bit better. Okay, what I'm going to do is I'm just going to redraw this vector. Probably the easiest way to do it around that endpoint. So I'll take my protractor, stick it on that endpoint. I'll go 120 degrees this way. There's 120. And then I'll draw a line from there up, and again I'm going to specify that it's 0.620. I think I'll just get rid of that one now that I've moved it. And now I'm going to draw this one with its tail at the tip of that vector. Once again, I'll grab my protractor. and set it there. And now I'm going to pull out what I know is in the direction of the pickup, and I'll rotate around 120 degrees and stop. Draw a new line segment, starting there, going down this axis. I'm going to specify that its length is 0.500 to represent my 5,000 newtons, and there it draws my line. So I'll get rid of that vector because I've now moved it. I'm going to take my construction lines out of here too to make things clearer. And now, all I have to do from this point is I have to draw a line from the origin, the tail of the first vector, to the tip of the very last vector, and that's the resultant. How big is it? Well, I'll just measure. I get 1.843 meters, which represents a 18,430 Newton vector. And what's its angle? Well, again, I'll just measure. So I'll select this at the origin, and then going from the pickup toward the snowmobile, I'll measure what's that angle. And looking down in the lower left-hand corner, I see that it's 3.2 degrees. So my resultant is 18,400 newtons at 3.2 degrees toward the snowmobile from the pickup.